Some of the most productive hydrocarbon reservoirs are those found in ancient deltas. This field, the Brent Succession, was discovered and recognized by scientists as being an ancient delta. What is it that determines whether or not an area is an ancient delta? Trevor Elliott.
In order to identify ancient deltaic successions in the subsurface and to predict the shape and trend of sandstone bodies which act as reservoirs, we need to understand something of modern deltas, in particular the processes which operate in modern deltas. But we also need to examine ancient deltaic successions, such as these in the Carboniferous of Western Ireland, in order to understand more of the deposits of deltas. Firstly, we'll examine modern deltas, but it's not that simple, as there are several types of modern delta.
The Mississippi is a river or fluvial-dominated delta. Large distributary channels transport vast amounts of sediment into the Gulf of Mexico. The Rhone is a wave-dominated delta. The front of the delta is reworked into a series of beach ridges that spread along the coast. The tide-dominated Ganges-Brahmaputra delta differs in appearance and structure. Here, the high tidal range causes sediment to be worked into a series of tidal ridges, which are cut by a network of large estuarine and tidal channels. The Mississippi is the largest river system in North America and has a drainage basin that covers most of the United States. It's one of the best studied areas of modern deltaic sedimentation in the world. The Mississippi is a broad, flat, marshy environment. This is one of the many interdistributary bays that make up its delta. Many of the vegetated areas that we see here began as open bays. In just a few decades, these bays have filled with sediment, and plants have taken root. Being one of the world's youngest deltaic systems, the modern Mississippi Delta has formed in the last 7,000 years as a result of numerous overlapping deltaic lobes. Each lobe has a life of 1,000 years. The concept is simple. The process begins when a lobe progrades seaward. The river abandons its course. The lobe then undergoes compaction, subsidence, and some reworking by waves, while a new deltaic lobe builds out in another direction. A more detailed picture of how this delta was formed is revealed by examining the present-day processes. The Mississippi Delta is composed of many sub-environments. This is an enhanced satellite image. These are the distributary channels which radiate from the river. They are the major systems of sediment transport. Next are the interdistributary bays which emanate from some of the major distributaries and are filled repeatedly as a result of breaks in channel banks. At the mouth of the rivers, the major deposits of sand form the distributary mouth bars. Further seaward, the finer sands and silts are laid down, forming the delta front. Still farther offshore, well beyond the continental shelf, the finest sediments are deposited, forming the pro-delta. Although this distributary channel looks man-made, it's a natural feature. Flanking the channel are the interdistributary bays. Much like the history of the delta lobes, these bays have a life cycle and are filled when there's a break in a channel bank. In the early 1800s, a break occurred, and during the next 150 years, a bay fill sequence was laid down. 20 years later, there was another break. Meantime, the older bay fill area underwent subsidence. These repeated processes of a break in a riverbank, a build-out, abandonment, subsidence, and flooding by the sea are the basic cycle of bay fill deposits. At the mouths of the distributary channels, muddy, sediment-laden fresh water flows into the Gulf of Mexico. It's called the effluent plume. The more buoyant fresh water floats on the denser salt water of the Gulf. As the sediment is carried out into the Gulf, the coarser grains are deposited nearest to the shore, forming the distributary mouth bar. The finer grains are carried seaward in suspension to the deeper parts of the delta front. Still further offshore, the finest sediments are laid down on the pro-delta. With time, deposition allows the whole system to prograde seaward and produce a coarsening upward sequence. The sand-body geometry of the Mississippi Delta shows well in this enhanced satellite image. Here, the bar finger sands follow the outlines of the major distributary channels. The Mississippi near and offshore environments are highly unstable. This is a mud diapir, or mud lump. Its creation is a result of high water and gas pressures which cause the buried muds to rise to the surface, forcing their way through the overlying sediments. But that's only part of the story. Recently, more of these features have been discovered. A closer look at the near and offshore sites near South Pass in the Gulf of Mexico reveals not only mud diapirs, but rotational slumps along which large masses of near-shore sediments are carried downslope and redeposited as slump sheets. Further offshore, there are growth faults which are situated at the shelf edge. For offshore operators, these unstable deformational features have contributed to a number of drilling problems, rig failures, and pipeline breaks. A different modern deltaic environment can be seen in the south of France. The Rhone Delta is located along the coast of the Mediterranean Sea. Its appearance and structure are different from the Mississippi. But at the same time, there are features which are common to all deltas. The distributary channel, the Grand Rhone, is the main source for sediment transport. The Petit Rhone is a minor distributary. At one time it was the major distributary, but it's now in the process of being abandoned. The delta front is dominated by very wide beaches and beach ridge complexes. Next are the closed bays. They contain more fresh water than the vast interdistributary bays of the Mississippi. Beaches on the seaward side act as barriers and close off the bays. These bays are shallow and filled with sediment from the channels. The channel of the Grand Rhône is almost a kilometre wide. Because of a number of large dams built upriver in the last century, the amount of sediment discharged into the Mediterranean has decreased drastically from 40 million tonnes a year in 1900 to 4 million tonnes in 1970. The Petit-Rhône's sediment discharge is considerable, given the fact that it's in the process of being abandoned. The Rhône Delta is influenced by dominant onshore winds from the southeast. These winds have reworked the sediment from the distributaries, and as a result, the major portion of the Beach Ridge complex extends west of the Grand Rhône. These beaches spread out along the coast of the Mediterranean, connecting the mouths of both distributary channels. The mouths and these connecting beaches have been prograding with time. The sand body geometry of the Rhône illustrates a pattern where the wide coastal sands are cut by fluvial-dominated channel sands. The Rhône's geometry is quite different from the bar finger sands of the Mississippi. The Carboniferous system of Western Ireland is a sedimentary basin partly filled with deltaic deposits, and its ancient outcrops may be interpreted through our present knowledge of modern deltas.
We suggested that deltas are important in the fill of this sedimentary basin. But how do we determine that a succession was deposited by a deltaic system? And, having established that point, how do we tackle the problem of what kind of a delta we're dealing with in this section?
This section reveals the three main sub-environments common to all deltas: the delta front, the delta plain, and the distributary channel. At the base of the cliff is a large-scale coursing upward sequence, some 60 metres in thickness. The sequence commences with mudstones and fine siltstones deposited from suspension, and passes upwards gradationally into well-bedded, higher-energy sandstones.